Ladies and gentlemen, I'd like to again introduce Adam Hughes. He is going to talk to us today about Zeta Functions and counting. So let's welcome Mr. Hughes.
Number one tip for surviving graduate school: don't let the professors smell fear when you enter there. They'll just tend to attack. Do we want to close this, Corey, for the sake of the people? Yeah, I'm going to say yes. There we go. Now you're all trapped in here with me. All right, so there's a classic sort of problem that you might ask yourself if you're a number theorist, or if you're just a math person in general who likes the interesting bits within math itself. That's what number theory is about. It's not about finding all the things in the world where you can find math. It's about finding beauty in the math itself. And one of the things that people tend to like is things like, determine the number of ways to write an integer n as the sum of two squares. It's not a g, it's a y. I'm just bad at writing. Right? Certainly not all numbers are expressible as the sum of two squares. We don't necessarily know that yet, but we will in a minute. I mean, you could also just say, the number 3, but, we're going to pretend like we don't know any actual numbers. So if we have some notation, we can, denote by R2 of n. This is the number of ways to write n as a sum of two squares. Fancy set notation, it does this. Right? And so, in general, this is a very hard question to figure out what R2 of n actually is equal to. Right? And the typical number theory approach to this problem is to say, all right, I don't understand this as a function, point by point. It's not like, it's sort of like, it's sort of like the sine function, right? I mean, in theory, you have a convergent series for sine that you all learn in calculus, but knowing the exact value of sine for a randomly chosen point is a very difficult thing. Most of the time, we don't have a way of knowing exactly. But we know sort of how sine behaves on average and some of its interesting properties, which is something we explore towards getting a better understanding of this function. Right. In particular, we want to perhaps know how things happen on average. If you look at R2 of 1 plus R2 of 2 plus R2 of n, you can visualize this and so on and so forth in all the columns as looking at the number of lattice points inside some circle of radius, say, r. Right? If I want to count up to n, then that's basically all the lattice. This is all the lattice points, because what's a point in here? It's an integer point, xy, in Z2. And since it's inside the circle, it satisfies x squared plus y squared is less than or equal to r squared. And if we said r squared equal to n, for example, then we can say that the number of points inside this is really a number of total things up to this point. Right, so this is a very fruitful way. Instead of looking at equals, we can look at less than or equals, and somehow this becomes easier as terms of a question to study. In particular, we can write sum I equals 1 to n, R2 of I is equal to number of solutions to x squared plus y squared less than or equal to n in Z2. And we're familiar with the Z notation for integers. I say, you guys are the super math people. All right. At this point, you want to say, okay, how can we figure this out? Well, in calculus, you learn something which a lot of mathematicians, I think, or at least early in their careers when they first take calculus, ignore. when you first do derivatives and antiderivatives, in particular antiderivatives, most of the time you see the fundamental theorem of calculus and you immediately say, oh great, you know, why do we bother with these stupid rectangles and stuff, right? But the rectangular approximation methods, first of all, are very important for theory when you get into math later on, and also can come into a lot of help in this case. If I do squares here, and one more. Right. If you look at this, you can use a rectangular approximation method to estimate the area of this circle. Again, imagine I'm doing this in all 4 quadrants. And you can note that each lattice point, if I look at the upper right corner, that corresponds uniquely to a specific, like this corner here corresponds to this square. And since the side length of these things is 1 each unit of area accounts for 1 lattice point on the inside here. So I can compare counting numbers of points with estimating area. In this case, I'm estimating from the inside, and I'm noting the ones that are completely inside here get these things, and then the ones which go a little bit outside, because part of this is, you know, the area of the circle, the disk is not exactly equal to this. It's bounded above by the total green plus purple area and below by just the purple area, which is what we're mostly looking for. And again, down here there would be some things which are, you know, green because it goes outside, but it would still count because we're counting upper right corners in here, so it's not always just purple that we care about. So this gives us the idea that maybe the area of the disk is a good estimate for the number of lattice points in there once it's scaled out there. In particular, since the area is pi r squared, and r squared is what we said would be about our n, you might guess that there's about pi times n of them on average, right? And so how can we get across this? Well, if you look, the diagonal length of this is 1, 1, and a right angle, so you know this is square root of 2. If I decrease my radius by square root of 2 and look at, you know, smaller circle, or increase it to look at a bigger circle, you'll notice that the bigger one contains all of the green cornered squares, because if you're connected to, if you're part of a square with any point inside of here, the farthest out you can be from there is another square root of 2. So even if you're right here on the edge, you can only go another square root of 2 out to be counted on a square there. So if I increase a little bit, I'm guaranteed to include all the green things and overestimate. And if I decrease, I'm guaranteed to cut out and only get purple squares. So what do? I look at pi r minus root 2 squared. That's less than or equal to the sum I equals 1 to n of r2 of I. So this is the sum I care about. This is less than or equal to pi r plus the square root of 2 squared. And lo and behold, this is pi r squared minus 2 pi root 2 r plus 2 pi less than or equal to, thing I care about, less than or equal to pi r squared plus 2 pi root 2 r plus 2 pi. Right? So if I get rid of the r, if I subtract pi r squared from both sides, I get that the absolute value sum I equals 1 to n r2 of I. So this is what I care about, minus, and let me write this as pi n, because n is my r squared, is bounded by something, some constant times r, which again I'll write as square root of n. Right, so you guys all know from calculus and limits that n grows much more quickly than the square root of n. This is somehow the right average, and what's left over after I take out the main estimate there is only something that grows much more slowly. Right, so this is true. This is the average number of lattice points you'll get up to this point. So if I divide by n, right, because again I want to say, like, you know, what's the average value of my function, r2 of I, this approaches pi as n goes to infinity. Now, interesting corollary. Let's look at so R2 of I is the number of ways to write something as sum of squares, right? Well, look at n. If I switch x with minus x, or, this is important, that's or y with minus y, I get other representations, right? Because integers, you're allowed to do these things. Which means that if R2 of I, or let me say R2 of n is greater than or equal, or is greater than 0, so if there's any possibilities, then R2 of n is greater than or equal to 4, right? Because I could switch these things independent of one another. But then if the average value of pi, we know that pi is less than 4. You all remember that, I hope. But then if I'm averaging less than 4, there must be some numbers which I can't express as sums of two squares. Because if all of them were there, if all of them were non-zero, then all of these terms would be at least 4. So there must be numbers, in fact, a lot of numbers. There won't even be like all numbers after a while are expressible as sums of two squares. There are infinitely many numbers, and they take up a noticeable amount of integers, cannot be written as the sum of two squares. And we get this all just by knowing that pi is less than 4. Right? You can figure this out. I mean, you could, like I said before, you could choose the number 3 and say, oh, 3 is not the sum of two squares, so we can't write all of them. But this tells you more than that. It tells you that there's lots and lots of them that you can't do this for. Because if there were finitely many exceptions, this limit would be 4. All right, so this is some of the general ethics, or ethos, I suppose. It's not really ethics. It's really the ethos of number theory, is that you have really hard questions that are hard to answer using algebraic methods or direct observation of the function. But if you look at things like this from a more, I guess, a statistical standpoint, where you're looking at averages, there's things like standard deviations and things like this. Treat these things, instead of being cool numerical functions about natural numbers, treat them as if they're statistics about the natural numbers. And then they can tell you qualitative information like existence, or in this case, non-existence theorems. And you do that just by doing things, again, I really like this approach because it has a nice geometric flavor to it, it has a little bit of analysis flavor to it, and of course it starts off with a very simple algebraic flavor to it. In fact, the problem is so algebraic in nature that when you delve deeper into the algebraic side there, you can use this result to tell you interesting things about algebraic things.
Oh, I have a question.
Yeah.
Sorry if this is kind of stupid, but so you know n is an integer, right?
Yeah.
So like, I mean, so how do you know that all the lattice points matter? Because not all the lattice points are going to get hit if you take a radius that's an integer, right? Or maybe I'm...
No, yeah, I see what your question is. So, yeah, you're right. I'm not going to land on these lattice points all the time there.
Right.
But I mean, the point is really to add. I mean, if say n is 5, right? Then maybe r is 5 plus, I don't know, square root of 2 over 2. Right? That's not a big deal. I just only count up to 5. Right? So if this thing's a little bit farther, that's not really a problem. The reason I choose specifically to let r be things besides just integers there is that when you do this sort of limiting process, you want to be able to subtract them. Because it doesn't really matter if the circle is a little bit bigger or not. The point is that if once I go another square root of 2, I'll hit another integer lattice point anyway.
It's an approximation.
Yeah, exactly. It doesn't need to be. That's one of the nice bits about it. It doesn't have to be an integer because integers are sort of, they happen at regular intervals. In fact, intervals of 1. Mm-hmm. No, that's a good question. That's another thing I guess I should espouse about analytic approaches to number theory is that when you do things this way, you get to use all the power of things you learn in calculus or real analysis or many times complex analysis to deal with problems about integers, which are much more discrete objects, which are, I think, most students get introduced to as an algebraic object first. That's one of the beautiful things I think about number theory as a subject. You're not really limited by the same things you would be in a lot of other areas. You can freely move between algebra and analysis, and things make sense still because you don't have to worry about weird contexts like, does this PDE I'm dealing with have to deal with this particular kind of water I'm applying it to. I'm not overtly slanting PDEs. I'm just saying this is a practical concern you have to deal with in them, in which you don't. All right, so there's our classic problem, and there's sort of our our interesting bit about averages. So now how does this relate to other things? The progress, and I'm still bitter. But suffice to say, that's a really smart idea, because that is about, right, taking something you don't know, connecting it to something you do know, and doing the thing you do know until you get results in the thing you don't know. In general, calculus and analysis is a well-studied thing because of the continuum nature of the points, because of the completeness in a lot of spaces you deal with. You can take limits and do all these intricate analyses with integrals or integral estimates, and you can usually use that to figure out values of things like this residue. Like, again, this is a limit of a function times another function. Right, s minus 1, obviously, but you can actually compute values and make a table like they made you do on the first day of calculus, because unlike all the other calculus problems we gave you, this one doesn't have a simple, easy solution. But you need to numerically estimate it. But that, for once, that numerical estimate is very useful, because it tells you what you can expect on average. Oftentimes, you can use this for computing like percentage of the time things work and other related things. First, so now I'm going to explain why I cared about this limit being 1 before. This limit being 1 before, I know I already did that. I told you, because yeah, that means there's one way to write n as n. I care about this limit because it's about approximately the number of ways to write n as x squared plus y squared. There are about pi ways to write every number. And of course, this is one of the great jokes of statistics, right? On average, I can do this about pi times per number. And of course, well, how many numbers can you do it exactly pi for? Well, none. It's not a counting number. That makes no sense. So for precisely 0 numbers, are there pi ways to write it as the sum of 2 squares? And yet that should be your expectation for any randomly chosen number, that you can probably do it about pi times. If you demand, for example, that these things be relatively prime, so like instead, I can't put 2 and 4 in there, I'd have to do like 2 and 3, you'll actually get a factor involved like 6 over pi squared, which is zeta of 2 for those of you, oh sorry, not s. Zeta, the Riemann zeta function of 2. This relative primality has to do with this number here. And you can do a lot more intricate analyses by tweaking the function R2 of n to be a different choice of function. And it's a very interesting idea. This analysis sort of goes through in general. But why the -1? And this is where I pander to the algebraists in the audience. I'm sort of a universalist. As a number theorist, I do many different areas of mathematics, probably more than most in terms of interaction. I hesitate to say more than any because that's a universal statement, and as a mathematician, right, you make sure you got to be careful about those. But if you look at things of the form a plus bi, which are in what I call z adjoin I. Those of you who don't know, this is in it. So this is the set x plus yi. X and y are integers, right? If you treated my plane from before as C instead of R2, you could treat these as points in the plane. It turns out that this is a very interesting object algebraists call a ring. Again, I don't know what your guys' background is, so if I'm being pedantic, I apologize. But if you look in rings that are this and like this, there's a function called a norm on them, and the norm of a plus bi is actually a squared plus b squared. And since this is associated, so the -1 has to do with the fact that I squared equals -1. Right? If I were to write zeta -3, then I would be dealing with something that has to do with the fact that 1 plus the square root of -3 over 2 cubed equals 1. This is a 4th root of 1. This is a 3rd root of 1. You guys learned about these, I think, back in like pre-calculus when you did basic complex numbers. -3 is sort of special. But you can deal with a lot of different things like this, and you index them like this. They're things which, when you look at part of them at least, they square to the number down here. For those of you who were at my last talk, I talked about quadratic reciprocity. You can actually use quadratic reciprocity to find out that you can connect R2 of n and write it as the sum of this thing. And again, this is the part of the talk where I get to talk about really weird things. Chi, let's see, d divides n, d 4. It's called a quadratic character modulo 4. And you can actually write the number of squares as a sum of plus and minus 1s, depending upon the primes that divide n and what they are, modulo 4 and modulo all all the modulo 4. So you can not only so using this connection here, you can understand how this quadratic character behaves on average. It's related to something called an L function. You can figure out you can actually figure out from this that if you look at n as 2 to the k times p1 to the e1, pk to the ek, q1 to the 2f1, qj to the 2fj, and that shouldn't be a k, because I already used a k. Actually, let me change this to an n. No, not an n, m. There we go. That if all the qi are congruent to 3 mod 4, and the pi can be congruent to 1 mod 4, and 2 is 2, if this is the prime factorization, you can write it as a sum of 2 squares, and this can tell you about, and that you can find that out based on the behavior of this character. These are more advanced techniques. This is the main thrust of things there. But this is sort of to give you a flavor of how you can talk about things which are squares modulo p for different primes, so as you know modular arithmetic. And suddenly we have all this analysis work we've done having repercussions in terms of modular arithmetic, in terms of basic group theory, in terms of rings, and this is associated to fields. This is a very flexible approach for connecting heavy analysis to very heavy algebra, especially those of you who know the sort of right way to phrase quadratic reciprocity, which is an enormously deep fact. So that's sort of that's the main gist of my presentation. Are there questions? I say we had some during the talk. So. All right, cool. Meeting adjourned.
The chi-sub 4 there was just any character of sigma 4 star?
There should only be one.
Oh, yes. Okay, wait, so that would say that you had that R2 was, so you had that R2 was the